we are going to begin a series on induction motors. Mark, why don't you go ahead and get us started talking about induction motors?
Well, to begin, no type of motor is more pervasive and important to the electrical industry than the induction motor. Certainly, and when I say electrical industry, I'm including the mechanical, all the people who are actually end users of these motors. There's a big section in the National Electric Code addressing this type of motor and how to deal with it. And so we're going to go through it in relative detail, but in small bites. There's an opportunity here to understand induction motors well enough that you can understand what the National Electric Code is trying to do with all of its rules.
What is an induction motor?
Well, an induction motor is the clever invention of Tesla. That was a really smart guy, and he and Edison were vying for who was going to be the dominant player in the day. And Edison had DC motors, and Tesla looked at, well, the way the story goes, he was thinking about the moon and the tide and the rotation of the earth. And he was thinking, if the moon and the earth can make the tides rotate around the earth, why not use magnetic fields to make a rotor rotate? So he came up with a three-phase power system that rotates and drags a rotor along with it. And the reason it's called an induction motor is because the current in the rotor is induced, so there's no brushes. Edison always had brushes on his DC motors, and they were a high maintenance item. And Tesla got rid of the brushes and said, let's just induce the current in the rotor and make the motor much simpler and more reliable.
What were these brushes in Edison's motor doing?
Well, Edison, since the motors were DC motors, there was no way to induce any kind of current. So he had to transfer the current to the rotor to make the magnetic field in the rotor. He had to do it directly with some sort of a conductor. And as the industry developed, they became the carbon brushes. They were spring-loaded, rubbing against a commutator that was usually made of copper. And it would wear out eventually, and you'd have to maintain it, replace it, whatever. And Tesla got rid of that altogether. By the way, we still have DC motors with brushes and commutators. If you've got an old electric drill, that's the way it is. If you were a kid and you built the little Boy Scout DC electric motor, it had brushes on it of a very crude form, but they were there.
I see motor speeds of 3,500, 1,750, and 1,150 as common RPMs. It seems they should be like 3,600, 1,800, and 1,200 if the armature follows the magnetic field. What's that all about?
Well, now we're getting into the real physics of the induction motor. Let's start with what makes the difference between speeds. The speed is a function of the number of poles in the motor. A two-pole makes it go as fast as it theoretically can, which is 3,600. And where does that come from? Well, if it rotates once every 60th of a second, and you've got 60 seconds in a minute, 60 times 60 gives you 3,600. That's where the 3,600 comes from. If you have four poles, it rotates half as fast because it has to catch a pole twice as many times around. And now you're down to 1,800 RPM. And you can add more poles, get down to multiples of the poles, and 1,200 is another speed. So,
okay, that makes sense. But what's with the 3,500 and the 1,750?
Well, that would be a synchronous motor, and these are induction motors. And the induction motor can only work if the rotor is slightly behind the magnetic field rotating around in the stator. And if it isn't behind, well, then there's no difference for a magnetic field to develop any current, and therefore you've got no power in the motor. So once you get up to full speed, if you actually get up to synchronous speed, there'll be no current flowing anywhere. And that obviously doesn't do any work. So the induction motor has to run a little bit slower than the ideal speed.
Is there a limit to how slow an induction motor can operate?
Yes, when the motor runs too slow, it lags too far behind the rotating fields, and the torque and magnetic attraction collapse. The difference between the ideal rotation and the speed is a term called the slip speed, and just visualize it as the rotor is slipping behind. And so if you're at 3,500 RPM on a 3,600 ideal speed, well, that's a slip speed of 100 RPM. Same for 1,800 and 750. That's a 50 slip speed.
Okay, this has been a lot of information. Is there more to know?
Oh, there's a huge amount of information on induction motors, and let's save that for the next podcast.
All right, we'll wait. Let's review what we learned today.
Okay, the induction motor is the workhorse of the mechanical world. And as electrical engineers, we have to learn how to connect properly to an induction motor. It rotates to follow the stator magnetic field, and thus the speed is multiples of 60 hertz. But as we learned, it's not quite 60 hertz. It's a little bit less because there's a slip frequency, and we'll start getting into that as we move along.